in a way, it kind of feels like coming back to some of the original questions that I've had already in the past, I think, in terms of the expectation value, in terms of interpretations of things just like multiplication, right? So in the formula, in the continuous formula, although it's a very specific case, because in the continuous formula, it's a multiplication by the conjugate, by the complex conjugate, or whatever you call this guy. So in a way that is by definition that is like squaring, right? I'm not so sure what is there an interpretation of complex conjugate wave function? The complex conjugate of a wave function is representing a recurrence of I in that function with minus I. Okay, yeah, exactly. But in a way, what's the, other than just being a tool, right? Complex numbers in all predictions, because of the product is always a real number. That makes sense. Intuitively, complex function of a wave function describes a time reversed wave function. Okay. But if it describes a time reversed wave function, then what is the point of these? Just even forget the operator for a second, and then what is the point of what is sort of an intuition that you have about multiplying these by its conjugate, other than just saying, the intuition is I'm squaring it because you want the probabilities. I think that's where this really comes from. I think it's less than, now that I think about this, less than the I don't know, I'm looking at OBS and this screen looks like burnt white. I hope that you can see that better in the video. It looks awful. Anyway, so in a way, it's like what you're trying to do is you're trying to say, I'm gonna square it so I get the probability distribution, and then I'm going to integrate. Yeah. The integral part is still another question, but I think that could be because it's like, where is the complex conjugate of a wave function? But still, this is still a question that actually, in terms of first principles, in terms of like core definitions, kind of bothers me a bit, which is like, why is it that squaring the wave function to get the probability distribution, it's done by multiplying by its complex conjugate? Is it just pure tooling, or I mean, it's not that that's the definition of squaring, it's that that's the definition of the absolute square, right? But other than saying later in this section, you will see how to use the wave function to describe particles that are free or bound by forces to other particles. The specific form of the wave function depends on the details of the physical system. A peculiarity of quantum theory is that these functions are usually complex functions. A complex function is one that contains one or more imaginary numbers. Experimental measures produce real numbers only, so the above procedure to use wave functions must be slightly modified. In general, the probability that a particle is found in a narrow interval at a time t is given by, so you just dropped in here with a formula, then what the fuck is this, right? Like absolute value of the square is the complex conjugate of effect. The complex conjugate of effect is obtained with placing this present. Sure, that explains what is it doing, but not why is it useful. Consider notion. Okay, this is an exercise. Expectation values. That is the fucking problem with this shit, you know. It's just like, it's not really they just drop these things, right? But you still need, I mean, it doesn't tell you, it does not really satisfy my curiosity, I think, deep enough. In classical solution, the question is the function of measure of quantity suggests position is time. Note that the particle has one value of position time. As a wave function, the particle has many values of position of time, and only the probability density of finding the particle can be known. The average value of a large number of particles with the same wave function is expected to be The reason for this will become apparent soon. Okay, let's see. Formally, X is called a position operator. Symmetric and simplified calculations. Okay. It suggests the rules of classical mechanics and approximation of the rules of quantum mechanics for systems with very large energies. But classical mechanics describe only the latter. Sure, but that does not explain. Okay, so let's put down a wave function to the right, and then those are multiplied by the complex conjugate. Yeah, that is actually important. Or not, because we should not forget this X, because here it says the sandwich, so the momentum operator must act on the wave function to the right, and then the result must be multiplied by the complex conjugate, of the wave function on the left before integration. Awesome. But I mean, with DP is used of the X to indicate an infinite, in some cases we notify function position, but seek the expression momentum. The procedure for doing this is so you're changing the operator. Sorry. So two things that bother me here that I'm kind of stuck at the moment, which is the expectation. So which is first of all the concept of multiplying an operator with a wave function. So that's one section of it, and then the concept of what is the intuition behind the sequence of operations, right? So give me a second. I heard the vacuum cleaner turn on. I'll pause this. Doesn't look like. Anyway, hopefully that it's not gonna kill anyone. Where was I? So the complex conjugate is like, okay, I get this intuition. Let's work from that perspective. If you're reading through, should be for any given function. It's complex conjugate. The same thing is just completely answered in my hand. So for every x and t is a complex number, is the conjugate of that number, no more, no less. The reason it seems like sometimes it's only the t part that gets conjugated is simply that often it is the only part of a function that is complex. Those are examples. I remember doing this exactly. But what about the intuition? So intuitively, complex conjugation of a wave function describes the time reversed to wave function, traveling backwards in time as described by Sophie above. From a mathematical perspective, symmetry operations in quantum mechanics are either deemed to be unitary or anti-unitary. The time reversal operator is anti-unitary. Okay, that's interesting. So what is anti-unitary then? What does this actually mean? I should have ChatGPT open for this kind of stuff. Should actually pin it. Not really gonna pay for it though so far, although it's helpful. I'll take that off screen, so make sure that no credentials get revealed, if any, because I'm using the Google sign-in anyway. Close. So, what is an anti-unitary operation? Mr. ChatGPT. An anti-unitary operation is a type of linear transformation that preserves the inner product between vectors, that reverses the orientation of the space but reverses the orientation of the space. In the front terms, an operator U is said to be anti-unitary if it satisfies the following conditions. U is linear, meaning that it satisfies the proposition principle. Use an isometry, meaning that it preserves an inner product between the vectors. U is anti-linear, meaning that it satisfies the property that for any scalars A and B, but okay. To be honest, I don't know. Anti-unitary operations are important in physics, particularly in the study of quantum mechanics, where they are used to describe the time reversal symmetry of certain physical systems. Some common examples. Okay, cool, that's good, but it doesn't really tell me anything. Doesn't really tell me anything. How much does these cost? How is the upgrade plus? It's $20 a month. It's expensive. And I think Ghostwriter and Replit, you can't yet chat with it, can you? Replit, I think you can't yet chat with it. I think that's somehow upcoming. Anyway, but I just have to get used to these better. I have to get used to using these models better, because actually that's a much better way to ask this kind of stuff. Googling is also good, but Maybe I could try Bing. Why not? Could try Bing, to be honest. Should I try Bing? Because Bing has it integrated now in search, so that'll be quite cool. I'll do that next time. Anyway, okay, so let's try mapping some stuff in here. So, I mean, what I like about ChatGPT is you can actually store some of these chats now here as well. Like mode, oh, complex conjugation of wave function describes the time reverse wave function. But where are we stuck? So I'm stuck with the fact that so what are the pieces we're playing here with the puzzle? So okay, so we understand intuitively what the complex conjugate is time reversal, whatever that means. Okay, but it's somehow symmetry, right? Can you plot me? Can you plot me a simple 1D wave function? I don't know if it can plot me, or at least just give me the code. So when you multiply those, let's go to Replit, and we have exercise, kind of mechanic exercises. Should I just have just here. Unpin, unpin this. Okay. Can you give me an example? That's complex. I know it's gonna understand that. But essentially, that what this means is you're taking an operator, you're multiplying it with a wave function, whatever that means. That means applying, right? So mathematically applying an operator in quantum mechanics. What I like about using this kind of stuff is that it actually, yeah, okay. So this will generate two plots. So what if I run these? I think I had the same issue before, and I solved it by using these lines. Well, ChatGPT told me to do this like that. So I need to do this and now run this thing. Matplotlib is not defined. Ooh, what have I done? Whoa. Why isn't that working? Can I just do this? Can I just do this? I think so. That should work. Oh, really and imaginary. can you give me or can I calculate? Oh, well, the complex conjugate would be so what's the complex conjugate of this guy? I guess it's just with a minus, right? It's just, this is it's pretty cool. It's pretty cool because it's just a very different way of searching stuff. Oh, cool. So actually it gives me the NP conj. Okay, cool. So this is one output, and okay. And if I just say basically it's awesome. This is fucking awesome. Okay, it just suggested that. Cool. And then now can we just plot the so what is it actually gonna do if I run this? Boom. Okay, so there's actually an overlap between the blue and the green, I guess. It's both real parts are the same, but then the yeah, if I, you see, the thing is they just cancel each other probably. If I say so it's probably just y times y conj, and then you know, instead of just plotting these guys, I'm just gonna plot mole. God. So I think that's just gonna be, yeah, the one is 0, the one is 1. So the imaginary parts cancel out, which makes total sense, right? Or at least it's but I don't know why. What have I learned from that? Nothing really. It's just that essentially the complex conjugate is sort of, okay, it's used to kind of it's used to talk about like time reversal symmetry. Now why is the expectation value these essentially? What's the explanation, right? Where was I? This is where I'm kind of stuck. Where was I here? Quora. It's the death of Quora, by the way, actually. Maybe this is gonna help us. Okay, anyone's feeling like they can't handle physics, you should probably just leave now, because I'm multiplying the wave function by its complex conjugate. That's right. She just got yeah, why? So to something you can observe in the expression by measure for the percentage of the value is defined like these. So this is supposed to be interpreted as the average value of x that we would expect to obtain from a large number of measurements. Now the measurement itself is applying the operator, right? So Oh, wait a second. So let's just think in steps, right? So if you've got a wave function, applying the operator is something that we need to open up here as a box. But let's imagine that we understand that applying the operator means that you're in a way evolving that wave function, right? So you're changing that wave function. So that what? Like it gives you another function. It will give you another function, right? Essentially, it will give you a function that that roughly tells you what it's like. Applying the operator, mathematically speaking, is like the measurement, right? I mean, at least that's. So how do you GPT? How do you mathematically model quantum measurement? So is it by applying? So you apply the operator. So if you apply the operator, then you have something else, and this something else you then multiply it by the complex conjugate of the original one. In a way, I'm trying to think of like applying things, right? So if you think about you have the function, then you apply something, so you're kind of evolving that, and then you're doing a time reversal. Maybe that's what the multiplication would mean, because if you have a wave function and then you apply the time reversal, then the actual complexity or the complex part kind of cancels out. But if you've done something in between that, then that doesn't cancel out at all, like in a way, right? So at least, so kind of use present. Kinds of observables represented by self-adjoint operators in zero space. Eigenvalues of an observer correspond to the possible measurement outcomes, and the eigenvectors corresponding to the eigenstate. So given an observable, there's eigenvalues, eigenvectors. So you start with psi, and then you compute the projection of the state into each of the eigenvectors. Okay, so you compute the projection of the state into each of the eigenvectors. So you're doing a projection. The probability of measuring the ith outcome is given by doing these. So then if outcome 0 and 1. Yeah, okay, but that's kind of the same. Maybe it helps me to understand. Maybe I do have to actually unpack what the operator is, right? How it is constructed, because maybe that's the structure that is exploited in here. So, do you know what I mean? You know what I mean? What time it is? Sadly, I think I have to go. I have a bit more time to think about this. Yeah. So that's the step that I was missing, but it's fine. I mean, so this operator is doing something to the wave function. It's transforming it into something that is expressed as maybe the way you understand that is something that is expressed as sort of the eigen, like, yeah, coefficients of the operator, right? Not coefficients, but like some things with the states, with the eigenvalues and eigenvectors, with the eigenvectors. And then when you multiply, you see that is this, like that step in here is what kind of, so the concept intuitively, what it means to apply or to multiply the complex conjugate to that thing. Essentially it's just you're saying you wanna kind of cancel out something, but then you leave the effect of that x of that operator. You know what I mean? I'm just like, and that's probably wrong, but that's currently what's in my head. As in, like, you start off with a wave function, you modify it with the operator, and then in a way, when you multiply it then with the complex conjugate, what is happening is, could you say that you're sort of applying a time reversal thing, symmetry, whatever it is, but then because there's been this operator applied, this is what that operation is uncovering. That operation is uncovering basically somehow the coefficients. We should try to do an example. The problem is, I'm not so sure if I know. Can you give me an example? So can you calculation? So I wanted the continuous example. Can you give me a concrete continuous example? Continue, whatever, however that's written. I hope he will ChatGPT will understand what I mean. I don't want a discrete example, because that's just a discrete example. I want a wave function on the sort of on the real line. A continuous observable. Suppose we have a quantum harmonic oscillator in the state, and when to measure position x. Okay, I like it. Position x is alpha joint. Yeah, cool. The wave function of the harmonic oscillator can be written as position basis. So we have an example. What? The wave function of the harmonic oscillator can be written in a position basis as wait a second. Is it just notation that I'm not following? I'm not so sure that's right. I think this is right, but so you have a wave function, and to write it in the position basis. Okay. It was the first time I see. It's the first time I see something written like these. So I'm a bit hesitant to trust that. Because what is that anyway? Like, what is that anyway? The wave function? It just maybe refers to the wave function, right? In general terms, but it's got to be written as a function of something, isn't it? This is what makes it hard, right? Because sometimes I'm not so sure what the specific notation exactly means. the rest seems to check somehow in terms of the probability, squaring it and then the absolute value, blah blah blah, and this thing also makes sense. But let's look at these a bit more in detail. So it's the marker can be written as a position basis. So essentially what this is doing is, yeah, when you're doing that, you're applying the position operator, aren't you? Because the complex conjugate of that is, I think it's just the other thing, right? So I think it's basically, you just kind of flip it around, right? It's a complex conjugate of, but you flip the order as well. Yeah, exactly. Yeah. That's true, but so essentially, okay, so maybe all this is just, maybe I'm just looking at it from the wrong perspective. Maybe I'm just, because actually that opened up a bit the possibility that I'm just dissecting this from the wrong angle. You know what I mean? It's like I'm looking at this x in between, but this is just at least the way this is written here would make sense. It's like you think of a wave function, then you first you do is you write it and in terms of the position basis. That is what it means to apply the position operators, to write it in the position basis. Is it? But then here you already, what bothers me is that you already have some wave function as a function of position and time, and then you still apply the position operator. That's what bothers me. But here it's kind of like, it seems it's just some, and then you do these, and then you would think of the but still, then you're doing this kind of, then you're basically squaring the thing to get the probability, and that in a way defines the position operator. But that also makes no sense. I mean, it turns out after the fact that then you realize that if you decompose the operation, if you multiply this by this, you get in between the position operator, right? You know what I mean? Like if you're like if I'm doing these, God, if I'm doing these times these, essentially you end up with the position operator in here. I think that is the position operator, I think, right? Or that's a way to express it in bracket notation. Because a problem with all this formula stuff is that people tend to just get, work on them, simplify them, and then they're like, yeah, that's it. But then there's just no, it sometimes makes interpretation complicated. In this case, if I just dissect it like this is just a wave function written in the position basis, and then you square it, right? So you multiply it by its complex conjugate. That's how squaring works technically. You're getting the probability density function, which makes sense. That's what you want, right? You want to have that function that tells you what the probability is of each outcome, and then you can compute an average from that, or the expectation value. That would make more sense. But I'm not so sure. Could be an explanation. But it doesn't match with the fact that I see here this shit. Like you still see the x in here, whereas this psi is already expressed as a function of time of x. So my intuition would tell me, well, that x shouldn't be here at all, because you have the two things already. You know what I mean? Like this x just makes no sense. If that's how I'm going to interpret the whole thing, this just makes no sense at all. Why is this preview? The preview I'm seeing in OBS is extremely like overexposed. It's just really bright. I hope the video comes off better. Anyway, okay, I feel I've found kind of an angle to it. So that would explain, at least it starts to explain a bit more where these formulas come from. Yeah, makes a bit more sense. Cool. See you next time.